Hello, everyone, and thank you for attending today's webinar, Direct Electron Detection with Clarity, Viewing EBSD Patterns in a New Light. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or run out of time, you'll receive an answer later via email. We do capture all the questions. A copy of today's slide deck is available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulties, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I would like to introduce the presenter for today's webinar. Dr. René de Cloo has been working as an application specialist for EBSD and later also EDS at the EDAX European Support Office in Tilburg, the Netherlands, since 2001. His focus is on instrument demonstrations, conference and workshop presentations, and after-sales customer support. This includes on-site training courses, assistance with analytical problems, and scientific collaborations. Although focused in Europe, his work has brought him to customers and conferences all over the world. The international travel is a great bonus for his hobby, geocaching, where he tries logging at least one cache in every city he visits. As he has always been fascinated by the physical world around him, René chose to study geology at Utrecht University with a specialization in material science from a geological perspective. René's first introduction to electron microscopy and microanalysis came during his undergraduate thesis on deformation and pressure indicators in natural fault rocks from New Zealand, which involved a significant amount of SEM and TEM work. Later during his PhD thesis on nanometer scale melt structures in upper mantle rocks, he also learned about high-resolution TEM imaging and EDS analysis. Around this time, he also started using EBSD on a system without any automation. René's background in geology gives him a slightly different view on materials research, which has proven invaluable over the years at EDAX. In geology, one must often look at material without any prior knowledge on how it was formed. Applying this view to man-made materials can be a great help in explaining unexpected test results or materials failures that customers need to understand. Now over to René.
Thank you, Jonathan. Well, welcome everybody to this webinar on direct electron detection with clarity. Let's get started. So the layout of today's webinar, I'll talk briefly about a short history of EBSD detector development, because I can say, looking at EBSD patterns in a new light, let's have a little bit of perspective what the old light used to be. Then a few words on resolution in EBSD analysis. What do we mean by it? HR EBSD, HR patterns, HR scanning. We see lots of these things. People are talking about them, but what's what? Then a quick introduction in direct electron detection. How does it work? Removing optical artifacts, possible optical artifacts that we have on detectors. And of course, what can we do with EBSD mapping and pattern analysis with one of these detectors? Then I have some examples on low current operation, so seeing how you can use direct electron detection for very beam sensitive materials. And then a number of slides on the assessment of the pattern quality. So how different are they really with respect to a traditional detector? Let's start with the general development idea of EBSD detectors since, in this graph, the early 90s. And I joined here around 2001 when we could do about 2 points a second. And over the years with EDAX, I've seen the detector speed, the acquisition speed up to more than 4,500 points per second today. So a very strong focus on EBSD development, detector development has been on speed. And that includes new sensors, new types of detector detection mechanisms, optimizing the phosphor screens to optimize the electron to light conversion, lenses, optimizing those, fiber optic solutions we've used in the past. And all of that really helped us in bringing EBSD to the technique it is today as a almost standard tool in materials analysis. Now, with these really high-speed detectors today, that's just one word of caution. We can get really large data sets, but I just added a right scale bar here on this chart that in 1 hour at full speed, you can easily collect more than 15 million data points. And at some point, you need to think, how practical is it what I'm doing? You can get fantastic maps, but you still have to process them. So you still need to think very carefully about scanning strategy. Now, let's go back into the history a little bit. Early days of EBSD in a scanning electron microscope. This is an example from the 1970s, where people were using film mounted inside the vacuum chamber. You illuminate the sample, illuminate the film, and then replace the film, take a new one, and that way you can get fantastic patterns with effectively direct electron detection. In order to make this more approachable and user-friendly, the film was replaced by a camera, a television camera in the 1980s. And in order to get light into this camera, the EBSD patterns were generated on a phosphor screen. So the electrons coming from the sample hit the phosphor screen, get transformed into light, and then going through a sequence of intermediaries or an optical path into the camera itself. The initial cameras did not really have a high pattern quality, but it was live. You could see it on a computer screen, and you could actually do indexing between brackets on the fly with a lot of manual interaction. Then later in the 1990s, this is some nice example from some work from John Michael, looking at Yak Scintillators, so not a phosphor screen, but a different type of scintillator that transforms electrons into light. Get fantastic patterns with those. Not very sensitive. You need to have a little bit of patience to get these patterns, but they were really nice. And around the same time, the video cameras were replaced by SIT cameras, silicon intensified targets, to improve sensitivity and basically enable mapping. So we could get really nice EBSD patterns, and we could start scanning 2, 4, if you're lucky, 8 points a second, which was really nice to start mapping analysis and get texture information. Then late 90s, early 2000s, the SIT cameras got phased out, replaced by CCDs. Speeds started improving, starting again at 4 to 8 points a second. At some point, 32. That was 43. That was the first really jump in the performance of EBSD. And then later, 2010 to 15, with the CCD cameras, we could go all the way up to about 1500 points a second. And then quite recently, there has been a transition from CCD to CMOS, which allowed much higher speeds still for the data collection. So as I just mentioned in the chart, this is a pattern collected with a velocity detector that is capable of running up to 4,500 points a second. So it's a big, big improvement over those last 20 years. Now, just have a quick video to show what that looks like. It's always impressive to see what happens. So let me, if I can get the video started. There we go. Let's just capture an SCM image. And then when that is running, there's an EBSD map growing. So this is the actual speed. If you can read it on the lower left, It's running about 4,400 points a second. It's actually not going the fastest it can go because of the screen capture. But this way you can capture an EBSD map of about 180,000 points in only 40 seconds. So if I go back there, there's the exact number for this point, about 40 seconds, and we could get good data. Now, so far for the introduction on the EBSD detectors. Now, maybe something personal, but I've written a blog about this as well a few years ago, and that's the word about resolution in EBSD. People are using resolution in many different ways, and of course, an EBSD detector is a very important part of it, but what do we mean actually by resolution? Because some people look at resolution as a high resolution EBSD, and what they really mean then is high lateral resolution. So very small step sizes, perhaps go to transmission EBSD. This is just an example on a bulk material, 15 nanometer steps. You can get submicron particles very nicely. You could call that high resolution EBSD. Another definition of high resolution EBSD is orientation precision. So that has nothing to do with the distance between adjacent steps, but has everything to do with how precise you can measure an orientation and look at changes from one orientation measurement to the next in order to identify substructures, deformation structures, and understand your material. The third one that you could say high resolution EBSD is based on the number of pixels in the EBSD patterns. And you can see that as, do we actually see enough detail to distinguish specific orientations, to see enough detail to identify phases perhaps. And here I've just got an example of a pattern from biotite. There's an indexing solution. That looks pretty nice. And here's another one, and that looks almost identical. Now, in this example, it's the red pattern that's correct. And you can now see the high resolution EBSD as getting a pattern that allows us to get enough information to distinguish patterns like this for phase differentiation and perhaps specific orientation pseudosymmetry solutions. So if I put these three on one slide, there's high resolution on the left. For me, that is lateral resolution. The high precision as an alternative name to the high resolution EBSD for orientation refinement, for very precise orientation measurements, and using high resolution EBSD patterns, I would propose to call it high definition EBSD. So at least we know what we're talking about. I'm talking about this now because with the direct electron detection, we also want to look at very high, very small details in EBSD patterns, see what we can get that is maybe not possible with a traditional detector. So that would go towards the high definition EBSD side. Okay, now with that out of the way, let's go back to the last slide I just showed. There's the CMOS camera with the high speed. And what do all these detectors have in common? And that is that there is a certain amount of material between the layer where the light is generated to be detected in the camera and the sensor itself. And that unavoidably causes some degradation during the collection. So if you look at lenses, what can happen to your image? And it's sometimes really difficult to judge to what extent this is also happening on your EBSD patterns. You can have some kind of barrel distortion, as you can see here on the top left, or pincussion when the bands move inwards a little bit. Then you have some lens artifacts, spherical aberration, where the focus point is not the same from the middle to the edge of the lens. Of course, we always try to get the best possible lenses, but we also try to get the best sensitivity. And the best, most uniform lens performance is when you use the center of the lens as much as possible. The more you go towards the edge of the lens, the more deviation you may get from the ideal imaging. So those two parameters actually clash. We want to have a nice sharp image, and we want to have high sensitivity. Now, another one is chromatic aberration, which means that if you have light or a signal coming in, electrons or light with different wavelength, that they respond slightly differently in a lens and give an image at a different focal point. So that may make your image a little bit unsharp. And then there is astigmatism. That's, of course, well known in electron microscopy, where the beam doesn't go straight through. The beam shape is not circular anymore. It gets flattened in one or the other direction, and you get a disk of confusion where it should have been in focus. So those are just a few things that might happen in your EBSD detector that you are typically not aware of what happens. And some more things, of course, it's not just the distortions, it's also a signal loss by whatever tool you use to transfer the light into your sensor. And there's the scintillator screen itself. There are different types of phosphors. Here I have just a general composition of P22G and P43 phosphor screens. There's not really phosphorus in there, but it's the phosphorescent effect that transforms the electrons into light. And you can see that they give out a certain range of wavelength for light. And that light is then going through the lenses and having the narrowest wavelength reach as you want. That gives you the sharpest response from the lenses. So all of these, also a Yak crystal that you can use, are giving light in the green wavelength domain, which is also where the detectors are the most sensitive. Then you also have some thickness variation that will give you some effects on the sensitivity for high voltage. So if you go low voltage or really high, you have some effect on the thickness. And another thing is the grain size effect. So how big are the particles on your phosphor screen? And that basically also smears the signal a little bit in what finally gets to your detector. So the original signal coming from your sample going into your detector has a lot of hurdles to overcome before we can actually find it. Now, back to the future. This is really the focus of today's presentation, direct electron detection. It's not new. I've got a reference here on the right from Vespucci et al. From Strathclyde University in Glasgow, who've done some really nice work some years ago on direct electron detection and energy filtering on these EBSD patterns. But now we want to see if we can get it a little bit more general. So what do we mean by direct electron detection? Well, first of all, of course, it's removing the optical path. So finding a way to detect the electrons without using a phosphor screen or a lens system and getting the signal directly onto the chip. So as I mentioned before, a direct electron detection, of course, is not new. It's been widely used in mostly TEM analysis, low dose biological analysis because of its sensitivity. There has been some really nice work done to show that you can use it for EBSD applications, but as far as I know, it's always been very, well, limited experiments just to show that it actually is a really nice tool. Because it comes with a number of challenges. And one of the challenges is that the sensor is sitting on a printed circuit board, and the geometry of that board and just the whole shape of the thing limits what you can do. And that brings me directly to the solid angle. So how close is the chip itself? How big is the chip? how close can you get it to the sample in a safe way to get enough bands for good EBSD band detection and indexing. And another really important issue has been in the past is the temperature, because these chips get warm, and when you put the whole printed circuit board in vacuum, there's nowhere where the heat can go, and that basically limits the amount of time that you can run a detector like that when it warms up. So what we've done with the Clarity detector, we've built a direct electron detector with a, between brackets, traditional EBSD geometry. So it's a detector mounted on a tube that you can retract out of the chamber, so it's not interfering with the normal SCM operation when you don't want to use it, and where you can put it very close to the sample when you want to start using collecting EBSD information. There are multiple chips, in this case Timepics chips, 256 by 256 pixels, with a single top sensor. So if you look at the detector, it just looks like a single unit, a single chip, but there are multiple chips behind it. And the mounting in the tube allows for the passive cooling that we've added to make sure that the temperature stabilizes and that you can run it basically continuously and just run it overnight without any problems anymore. Now, just a little close-up of the detector itself. On the top of the image, you can see the silicon sensor itself. It has a very thin aluminum coating to block light, and that's where the electrons hit the detector. It's pixelated on the bottom side, and those pixels are connected to the Timepics chip underneath. And then, of course, you've got some wiring, etc., to take the signal out. Now, just to show what that looks like, this is a picture from the microscope I have here in the Tilburg office. There's the detector itself. There's a tube with the front end where the chip is. There's the sample. In this case, the stage is mounted on the door of the microscope, so I could not take a picture like this in color with the sample in situ, so I just put a virtual sample in there, but that's about the position of the detector, and it's between 2 and 3 centimeters away from your specimen. Now, here on the left, I have a little schematic of how it works. So here on the top, we have the silicon layer. Electrons hit it, forms electron hole pairs, and a bias voltage over this top sensor moves the charge into the chip underneath, goes into an amplifier, and then there is some thresholding to remove any electronic noise, to make sure that we're not just picking up random events, that we're really picking up the signal that belongs to one of these charge events. And when we have that, okay, then we can count an event. So basically we can identify single event detection with this chip, and we can count how many electrons we're getting. Now, how many electrons do we need to make a picture? Here I have an EBSD pattern, 20 milliseconds at 10 kV at 380 picoamp, and the maximum number of events in any one pixel is 50. So it's not much. And you can see the pattern is not brilliant. It's very noisy, but the bands are clearly recognizable. And if I show this in a three-dimensional plot, you can see that flat fielding has worked really well, and that the bands are not continuous, but they are just individual spikes of events that we have detected. But the band detection, if this is what you want to use in the Huff transformation, is very efficient in averaging intensity variations along lines, so brighter bands, and that means that we can, on a pattern like this, it's not a problem to find the bands and collect good data. Now, if we wait a little bit longer, you'll see that the noise level in the pattern goes down. So here I start at 20 milliseconds, That's 50 counts or 50 events, and here on the right it's 160. If I take a 20 kV beam, 450 picoamp, you can see as well there's a little bit more signal than a 10 kV, but the trend is the same. Get really nice patterns already here around 160 to 380 events between 10 and 20 kV. If I go up, you can see it just growing, and the information in the pattern doesn't really change, of course, but the statistics get so much better that you start to see a lot of detail coming in, and the individual noise peaks that we just saw in this 3D chart are disappearing, and the pattern is getting smoother. So here in the end, waiting about 2,500 events or 6,000 events, and we get really nice patterns. Okay, so that's a little bit of background in how this detector works. Now, what can we do with it? Of course, just normal EBSD mapping. Here's just a picture of an EBSD map of dual phase steel, austenite ferrite, under pretty normal EBSD conditions, 20 kV, a few nanoamp, in this case 50 points a second data collection. There's the indexing result, and we can just do any normal EBSD analysis we want. So there we have the phase map. On the right here we have the kernel average misorientation map, looking for the substructure in this deformed material. That's not too exciting, but it gets more exciting when we start looking at different currents, different conditions. So in this case, there's a map collected at 200 picoamp of current, which is a bit less than what we would normally do. And if you look here on the map on the left, the grayscale IQ map, you see that it's nicely sharp, and you get really nice orientation contrast and substructure in there. That's also reflected in the IPF map here on the right, where you can see the individual fields, small variations in orientation. And of course, we can also use this detector to collect our Prius images. Prius, in case you've not heard about it yet, it's Pattern Region of Interest Analysis System. It's a nice acronym, thanks to my American colleagues. I would never have come up with anything like it, I'm afraid. But if you look at the image, what it does is we use the EBSD pattern, and then we take a section of the phosphor screen, or in this case the chip, to extract the intensity at that part. And we're not trying to index anything, we're just using it as an imaging detector. And when we are taking the intensity at the bottom, we can get a beautiful picture, very similar to an FSD image, a force scatter detector image, but with the difference that this is background corrected. An FSD image just shows the raw signal. That's all the electrons coming in, including all the background intensity that we normally try to get rid of by background processing. And this picture takes that out and shows us the resulting orientation contrast. The location at the bottom of the screen or of the detector also ensures that it's very sensitive to topography. So on this sample, it's a cold pressed iron powder. You can actually see that at the interface between the larger granules, there's a little bit of depth there, some trenches along the grain boundaries. It's not been annealed, and that is really nicely shown. If you take a similar image, but then using the signal from the middle of the phosphor screen or the chip, then you get not as detailed, so you don't see the substructure so clearly, but you see the overall structures. The larger grain structures are very nicely resolved, and it's not sensitive anymore to topography. So the topography that we saw on the left image is almost gone. And on the top image, that picture is more sensitive to atomic number contrast, so material contrast. And in this case, it's also the holes and the topography that you see. But if you would have a multi-phase material, that would give you a really nice backscatter contrast image. And of course, because you could already see in the IQ map that the image is nice and sharp, also a kernel misorientation map or a map looking at substructures gives you fantastic resolution and sharpness in the misorientation between those, between the grains and different subgrains. Now, here is a small map around a microindent. Here on the left, you just see the SCM image. The indent has not been set nicely flat on the sample. It's been slightly oblique, so you see a little bit of cracking towards the bottom. So we just focused on the map towards the top. And if you look closely, you can see that there are small cracks emanating from the tips of the diamond-shaped indent, and also one from the left edge in the middle. And then if I look at the kernel misorientation map, looking at local misorientations from one pixel with all its surroundings, you can identify a number of low-angle boundaries that are curving away from the tips of the diamond of the indent, and also from the crack from the center left of this side, there is a low-angle boundary that goes all the way to the edge of this map. And this is a kernel misorientation map up to 0.5 degrees. If we then want to quantify the misorientations a little bit more, I've color-coded these low-angle boundaries, and the yellow are from 0.05 to 0.15 degrees, and in red, larger than that, up to 1 degree. And you can see those two yellow boundaries on the right, and you can just make them out in the kernel misorientation map as well. These boundaries have a misorientation of about 0.07 degrees. And this was an orientation measurement just using the Huff transformation. And you can get these really nice, sharp orientation changes also because the patterns are nice and sharp. Now, here are some initial cross-correlation results. The scaling is a bit different, but here on the left, the HR cam map, you can also make out the cracks at the tips of the indent, and also the one emanating here from the left edge. And then there are the stress maps on the left, looking at the rotation of the lattice due to this indenting. So I just want to thank Tijmen van Meij for doing this processing. And I'm working on some more information, some more maps as examples, and that will come in due course. Now, let's go back to low current mapping. This is a map at 110 picoamp, so it's about 1/3 of the low current pattern I showed earlier at 15 kV, 48 points a second. And although the patterns are really weak, you can see that here on the right, the indexing is not a problem, and you can get nice results of, in this case, a duplex steel. But of course, for a duplex steel, you don't really need the low current capabilities. You can easily go to a higher current and get better patterns and make your life a bit easier. But that's not always possible. So let's look at some more beam sensitive materials. And a certain class of materials that are being studied recently more and more are organic perovskites for photoelectric applications, optoelectronic devices. And I'm very proud that I can show you some examples from results from the work from Geda Adjaksa and Loretta Muscarella from EMOL from Amsterdam. So thank you very much for sharing this data and allowing me to show it. These are organic perovskites, methylammonium, iodide materials that are really very fragile, and they don't like the electron beam at all. So what can we do with materials like this? Let's start with this lead bromide material. There's the original pattern, and actually that looks pretty nice. And we do some extra image processing. This is at 15 kV, about 100 picoamp. And there's the indexing result. So with a little bit of extra processing, we can actually get really nice results. So here is the mapping area for this. On the left-hand side, that's an image without any tilt correction. Software knows it's not corrected yet, so I can stretch the picture to show the proper aspect ratio. And then on the right-hand side, we have the image quality map that comes out of there, and we can nicely recognize all the individual grains. And when I look at the EBSD results from that, indexing quality is good enough to really get nice grain structure, texture analysis. Here I just have a nice sharp grain size chart. And when I look at the orientation distribution, you can see it's almost all red. So in this case, about 95% of all the indexed points show a really good alignment with the sample normal along the 001 crystal direction. And when I look from the side, so this is an IPF map from along the x-axis, so in the plane of the sample to the bottom. Then you can see I got all these different orientations indicative of a fiber texture. You can see that also in the pole figures here on the right. The red image is from the plane normal IPF. That's the top pole figure where the 001 is sticking out, and all the other pole figures shows a nice circle. So it's just a continuous orientation along the sides. Now, that was one type of these perovskite materials. There's another one. This is an example from Loretta. And this is the SCM Image. It's a different type of production, flash infrared annealing. If you want to know more details, please look up the papers. It's just been published. And here you have the EBSD patterns as collected, and with some background processing, 15 kV, 100 picoamp current, 100 millisecond exposure, and this is easily indexable. So if I now go back to the EBSD map, so there's the yellow area is the analysis field, and there is the flower that you can just recognize, the IQ map on the left and the IPF map on the right. And the IPF map shows the crystal direction sticking out of the sample. In this case, there seems to be a very strong 112 alignment with the plane normal. If I just look at the different IPF directions, so in the plane of the sample is X, to the bottom, to the right, also in the plane, the Y, and then the Z. Again here, this seems to be a pretty nice fiber texture. But if you look at the pole figures, it's not completely random. It's not a full circle. There's clearly some symmetry and some preferred groupings in there. And when I then look at the orientations, you can see that this corner point of the crystal sticks out everywhere where it's pink, but where it's green, that's the side. That's the 100 direction actually. And it's almost as if this is a perfect symmetric growth in this microstructure. Now, then let's go to a slightly more complicated one, alternative method. So here we have really weak patterns. Same beam conditions. This is the original pattern. It's not too exciting. If you really stretch the contrast, we get this. And with a little bit of goodwill, you might be able to spot some bands. And then we apply a bit more image processing to that. And we can actually see something. And this is about the best pattern from the data set. So it's a difficult one to work with. And just to illustrate, so there's the indexing solution. This is the image quality map of the yellow rectangle. that you can see here on the left. And image quality is a measure for the brightness of the bands that we detect in the diffraction pattern. So when it's bright, it means that the software successfully identified a number of bands in the half transformation, hopefully also got an orientation, but at least it gives you some bright areas, but most of this material just did not produce any indexing results. And there's the indexing result I got with the patterns just as is without doing any additional processing. So we just have a few grains at the top here that are color-coded, and the rest really doesn't give us any information. Now, normally if you want to improve the pattern quality, you would like to use a longer exposure time or perhaps a little bit stronger beam conditions, so higher voltage or larger beam current. But for this material, that really is not an option because it just damages the material and all the crystal structure is gone. Now, what we can do, when we save all the patterns during mapping, we can use the tool we call NPAR to improve the results. And I just want to introduce NPAR if you haven't seen it yet. NPAR is another acronym. It stands for Neighbor Pattern Averaging and Reindexing. And what it does is we are storing all the patterns during mapping, and we're then looking at every pixel individually and the ring of patterns around it. It's like a moving average. So for every pattern, we are taking the 6 patterns around it, projecting those onto the central pattern, and getting an average pattern in the middle. And we index that pattern. And effectively what this does is it reduces it improves the signal to noise a lot. It reduces the noise in the pattern. And just to illustrate, there's the pattern again that we just had. On the left are the patterns after the original image processing that gave us a few bands and a few places to index. And the patterns in the middle, the two, are after NPAR processing. So you start to see bands that were totally invisible originally. And if we then stretch the contrast a little bit more for band detection, we actually get pretty good patterns that allows us to go for this mapping. Now, there's the indexing result. And if I index that, then this is the image quality map I get from the same area. And just to remind you, this was the original one. So we can just make out where they match. So there's in the middle, there's a few slightly brighter spots in the IQ map. Those were the really white areas in the new IQ map and towards the top. But we can actually identify the grain structure now in this IQ map. And if I look at the indexing results, it's not perfect. And there are still quite some areas where we don't get information, but we get a pretty good indication of the grain structure, of the orientation distribution of all the grains, and also of the grain size when we are looking at this image quality map. So if you want to know more about what this can do, look at the papers. I really thank Kede and Loretta again for allowing me to show this data. And it's a really cool application for low current analysis. Now, then let's take a look at the next step in what we can do with these detectors. So I was talking about pattern improvements. We were talking about removing the lens and phosphor screen and going for sharp images, trying to remove any artifacts. And this is just to illustrate what the difference is. Here on the left is a pattern collected on a Hikari detector at 1x1 binning. It's 480 by 480 pixels. And it's a pretty nice pattern. And then after collecting this pattern, I removed the detector, put the clarity detector on, and did exactly the same measurement with the same beam conditions, the same sample in the same spot using the clarity detector. And if you look at the image, you can see that the bands in the clarity pattern are clearer, are sharper. So let's see if we can quantify that a little bit. So if I go here, I just extract a few individual bands, and the small charts are band profiles across these bands. And the Hikari patterns are a little bit smooth, where you have very small details that you can see here on the right. So let's try a few more. There's that. There's a nice rounded band. It's still rounded in clarity, but a little bit of a lump on the top. And then there's another one. It's really rounded. Also around here with, again, some details. And these. And what you notice by this one, and especially by the last one, is the slope of these bands. So if you look at this pinkish band and this darker purple outline, just compare the slope of the central peak of the band and look at the edges. And you'll see that the slope on the clarity pattern is much steeper than on the Hikari pattern. So there is the broadening of the bands caused by the optical path into the chip. And when I just superimpose a few of those, I've just taken 3 of these bands out. And if you look at the round one, this rounded band here, this is the 111. Okay, that's nice and smooth, and they fit beautifully together. So there, you don't really see much of a difference. But if we go to 2 of the 113 family bands, so the pink one and the purple one, you can see that the clarity pattern shows a much more detail in these bands, and also that the peak shape or the band shape is narrower and sharper than collected with the Hikari detector. So because it's the same sample with exactly the beam conditions, it really shows you the difference in what happens in the optical pathway into the sensor on the Hikari against the direct detection of the electrons. Now, let's take a closer look at some of these patterns. You can, of course, just zoom in, but there is a finite number of pixels. What you can also do is just retract the detector a little bit. So in this case, there's the indexing. I just put a few zone axes on. And then I retract the EBSD detector, the clarity, to zoom in to the 231 zone at the top, and just to see what kind of details we can get. So let's get in. You can see the enormous amount of detail inside these bands where the bands overlap, and also the sharpness of the band edges. This is about 10 centimeters away. And just go back, there is the detail. There you have the original pattern. Next to it, the dynamic simulation. The image processing of the simulation is not exactly the same, but you can clearly recognize a lot of the details that we also see in the live pattern. And in some cases, it seems that in the live pattern, we see some more details even than what we can see in the simulation. I zoom in. So this was the final result. This was a solid angle of only 21 degrees. Do a dynamic simulation here. And here you can see that the simulation doesn't appear as sharp as the live pattern. And that is most likely caused by the energy of the electrons that is being allowed to contribute to the pattern. So we're assuming here that also the lower energy electrons can contribute, which causes a little bit of band broadening. And the live pattern doesn't really show that. Another pattern where I try the same zoom, it's platinum. And I start at 25 millimeter screen to sample distance. So if we zoom into the 111 axis, from a distance you can clearly recognize the threefold symmetry. But the closer you get, you can see almost like a six-fold symmetry here with the three main bands intersecting. But if you look close, you can see the band from the center top is showing like an arrow point on this circle, and the one to the right, coming in from the right, you see like almost a half moon shape bright band here. And that really shows the threefold symmetry in the details inside the band. You can also see it in the Holz rings that are present on the top, the bands from the top, from the lower right and the lower left. And the other three bands don't really have this circle available. So there you can really see the details in the bands. Now, I also tried to play with the energy thresholding. The standard setting, these are patterns collected at 20 kilovolts. Standard setting is we just use everything. So anything over 5 kV is allowed to contribute to the pattern. And so the pattern on the left has basically everything that we can get. And towards the right, the 17 kV, just means that I'm filtering out all the electrons with lower energies as detected in the chip. So that's the thresholding of the event counting that we got in the detector. And when I zoom in to the yellow area, it's not easy to see any difference there. You can see that the pattern on the left appears a little bit smoother, and towards the right it gets noisier and perhaps sharper, but not really on the band edges, but you can see some more details inside the bands. The fact that it gets noisier is caused by the amount of electrons that I'm removing by this filtering. The exposure time for this pattern here on the right is about 10 times longer than the pattern I have on the left. And when I zoom into one of the bands, so I just take this one, the red line is collected at the band that allows all the electrons to come in. The pinkish one allows everything that has more than 70 kV as detected landing energy on the chip. And if you look at the profile between those bands, they are virtually identical. There may be a slight change in width here, where the 5 kV pattern is slightly wider, which suggests that electrons with a lower energy can contribute to the pattern. But as just a back of the envelope calculation, it was not much that I lost in there. So it seems that the contribution of the low energy electrons is really small. Now, then the last few slides, this is on deformation, and just to see what happens with the diffraction inside the sample. This is a platinum pattern, and if you look in the middle of the pattern, the bands and all the details are really nice and sharp. But if you go towards the corners of the image, you can see that the details are not as clear anymore. They get a little bit blurry, especially towards the bottom. And if you look at the schematic to the right of it, you can see why that happens. In the middle and towards the top, the pathway of the electrons in the sample from the virtual point source where the patterns originate is relatively short. But towards the bottom of the detector, you have electrons that have to travel much further through the material to reach the detector. So on the way, there's a lot more interaction with the crystal, and that blurs the signal a little bit and also weakens the signal. It has nothing to do with any lens artifacts, as we might sometimes think for a traditional detector. It's really what's happening inside the material. If I look at a deformed structure, then it gets even worse. And still in the middle, it's the sharpest, but not perfect anymore. And towards the edges, the unsharpness really increases. So it's not just the interaction, maybe dynamic effects of the electron interaction with the crystal. It's also the additional path in a deformed structure that causes some more deformation and more bending or deflection of the electrons, causing the unsharpness of the patterns towards the bottom. Here's another, just a pretty picture. It's a niobium nickel silicide material. In the middle is beautiful and sharp, and if you go towards the edges where the path through the sample is longer, you can see that it just goes unsharp and you lose the contrast. And that's just an effect of the longer pathway of the electrons in the sample. Now, this observation led me to try another thing, and that was just looking at the specimen tilt, because you can normally do EBSD at sample tilt of 70, maybe 75 degrees. And that affects the distance that the electrons have to travel in the material. So here I have just a little schematic at 60 degrees with a relatively long pathway of the electrons from the virtual point source to the surface. If I go to 70 degrees, I keep the point of impact the same, then this pathway is much shorter. If I go to 80, there's again much shorter path and penetration depth of the electrons from the virtual point source to the surface. And it's that layer where the patterns are formed. So I tried to take a silicon single crystal, tilt it, and just see what happens to the EBSD patterns in such a tilt sequence. So this is at 50-degree tilt. You can see that the band contrast at the bottom gets dark towards that's negative. As again, there's a very long pathway of the electrons through the material. Towards the top, it still looks like normal EBSD patterns. And when I start tilting, I go steeper. This is about the normal position. And then we go a bit further, all the way to about 89 degrees, almost vertical. And if I play it again, you can see that you get more contrast in the bands at 70 to 80 degrees. And if you go steeper than that, a lot of the contrast disappears again, the band gets flat, and the band edges get very sharp. And that indicates, again, the amount of material interaction of the electrons. So you have just these patterns next to each other, where you can see the increase in band contrast, and towards the right, there's 85. It starts to flatten, then 89 I don't have on here, but then we could just see that the bands got very sharp and with very little internal contrast. And just to qualify that a little bit, this is the band profile of the 002 band. So at 50 degrees, there's almost no contrast. You can see the band growing to 55, 60, 70 degrees. Then at 75 to 80, you get a lot of internal contrast. So you start to get a lot of details in the bands. And if you go steeper again, then at 89, the edges of the band are steeper, so they're sharper, but there's very little contrast left inside those bands. So you could potentially use that also to model the penetration depth or perhaps the interaction volume of the EBSD pattern generation. Now, I've tried to do the same thing on the deformed sample. This is far more difficult because the moment you start tilting and you want to keep the same zone axis in the field of view, you have to move the detector or the sample up and down to adjust for this projection. So you'll see that the sample shifts a little bit. And an inherent problem in a deformed material is that the deformation is not homogeneous. So trying to find exactly the same spot for comparison was really hard. But what I tried to show is that at the lower tilts, the center of the pattern is really sharp, and towards the edges it gets a little bit more blurry. And with the steeper tilt, there is less variation from the sharpness in the middle towards the edges. Again, indicating the amount of interaction and the effects of any lattice deformation. Now, then, just to conclude, a few pretty pictures. There are some patterns I collected on some materials that I had lying around here in the office. So from very low atomic number, beryllium, aluminium, all the way to somewhat heavier material, platinum. You can see the effect of the atomic number on the sharpness of the EBSD patterns. The edges of the lighter materials are much sharper than when you go to the heavier materials, and that's a dynamic diffraction effect. But you can get really nice results on everything. So just to summarize what we've seen, the clarity detector is a direct electron detection system with a standard detector geometry for routine EBSD data collection with the normal geometry that we've been used to over the last years. The absence of the phosphor screen and lens system allows collection of distortion-free patterns, and any distortion that we see in the patterns really has to come from the material itself. It's not caused by any unqualified distortion that we introduce in the detector. It is suitable for EBSD mapping, but because it is also really sensitive, you can get indexable patterns with fewer than 50 electrons per pixel. You can reach analysis conditions for materials that we could not analyze before. So far for this webinar on direct electron detection, I want to point out a few additional resources from EDAX if you're interested in webinars or articles about different subjects. So you can register on this website. We also try to make some blogs every 2 weeks, so I encourage you to read those. I just published one last week again. There's a number of videos, of course. We are present on LinkedIn and Twitter. And if you have any other information, please don't hesitate to contact us and ask us at info.edax@amitech.com. And then a little advertising for the upcoming webinar in December is presented by our product manager, Matt Nowell. It's on the improvement of characterization efficiency for both EBSD and EDS applications. Thank you very much for your attention. So there is the last pretty pictures of the direct electron detector. Okay. Now, during the presentation, a number of questions have come in that we can, let's take a quick look what I have here. One of the questions from Jean-Luc Picard. What is the regular sample to detector distance you use with clarity? The distance, I'm always a little bit careful with putting the detector too close. When you have a traditional detector with a phosphor screen, it is not nice to hit the phosphor screen. You don't want to scratch it, but cracking a chip might be even worse. But in general, I want to put the EBSD detector close to the normal position because I want to have the same solid angle of detection to get enough bands for a successful analysis. Let's see. Some other questions I have here. Can we calculate dislocation densities using the CAM image? Well, not necessarily directly from the CAM image, but you can calculate dislocation density by looking at the orientation change from one pixel to the next. So we then know the distance between those points. We know the actual rotation of the grain, so we can calculate how many dislocations we need to identify or to accommodate that rotation. Then Another question here is about the direct electron detection. Do electrons damage the EBSD detector? No. The electrons hit the top surface, the silicon layer, and there we have the bias voltage, and it penetrates, what is it, a micron maybe, depending a little bit on the energy of the electrons that we come in. So the chip underneath is not directly exposed to the electrons that are hitting it. It's the silicon that catches the electrons, and then it's the electron hole pair that we are using to identify the energy and the brightness. So that's really not an issue. So then another question: how robust is the clarity? It is quite robust. The chip itself is much a harder material than a phosphor screen, but of course you don't want to scratch it. You will see some small effects if you would hit the aluminium coating on the front, just like on a phosphor screen. But yeah, it is sturdy, but you still have to be really careful. Then I think, I don't know, there's a number of other questions left. Let's see, what else do I have? Let's see. Then there's an application question, is how to improve the quality of a map for samples with a very fine-grained structure. It says what grain dilation parameters should be used. In general, when you want to analyze fine-grained materials, we need to look at the interaction volume of your electrons. And for EBSD, the interaction volume is pretty small. If you just imagine that the EBSD patterns or the electrons, when they hit the sample, they form a pear-shaped interaction volume that we often see with EDS. And the EBSD patterns are basically generated in the neck of that interaction volume. So the patterns themselves are coming from a very close to the surface in a very small area, but the pair underneath is contributing to the background and to the signal-to-noise ratio in the entire pattern. So in general, when you want to improve the lateral resolution for EBSD, it's a good idea to reduce the beam current. That will give you a much sharper beam, and that helps. The accelerating voltage helps as well, but not as much, because the patterns are still close to the surface, even at 30 kV. You have to find a sweet spot where you can really collect the patterns. One thing you have to keep in mind when you do that is that the patterns get sharper with higher beam currents, or higher voltages, sorry. So you can go down to 5, 6, 7 kV, but then the pattern contrast is not very strong anymore, and finding the edges of all the bands becomes more difficult. So if the patterns are really good to begin with, 5 kV is not a problem. But if the patterns are very weak to begin with, and then going to 5 to 8 kV, trying to optimize the interaction volume, that gets really difficult. So I have the best experience with a few hundred picoamp and 12 to 15 kV. I don't like going too low if my sample can withstand the voltage. So I hope I answer your question with that. Then I think I'm a little bit over time. It's 1 hour, 10 minutes. So there are a few more questions. I will answer these offline to you. And then I want to thank you again for listening to me and attending this webinar. And I hope to see you somewhere soon. Thank you very much.